Ever wondered how a jumbo jet, this massive metal bird, actually gets enough lift to fly? Or, how engineers figure out the speed of water flowing through a pipe buried deep underground? Well, believe it or not, the secret to both lies in one single elegant principle, Bernoulli's equation. Let's dive in and see how it all works.
So, here's our game plan. We'll start with what energy even means inside a moving fluid. Then, we'll get right into the equation itself and decode it piece by piece. After that, we'll make it super clear with a simple visual, see how engineers use it in the real world, and then we'll wrap up with the essential rules and a quick recap.
Okay, first things first, we have to talk about energy in fluids. It's really easy to just think, oh, it's moving, so it has energy. But honestly, there's a whole lot more going on beneath the surface. We're talking about hidden forces and potential just waiting to be unleashed.
And that brings us to the big question we're trying to answer. What is the relationship between a fluid's pressure and its speed? You might think they're totally separate, but as we're about to see, they are linked in this really surprising and fundamental way.
Here's the core idea you need to grasp. Any little particle of fluid that's moving around is carrying energy in 3 different forms. You can think of it like your own money, right? You might have some cash in your wallet, some in the bank, and maybe you own a car. It's all your wealth, just in different forms. For a fluid, this energy can shift between these forms, but the total amount of energy, that stays constant. And that right there is the key to everything.
So this idea, this law of conservation of energy, well, that's exactly what Bernoulli's equation is. It's the math that describes this whole process. So let's get into it and decode the formula.
And here it is. Now I know, equations can look a little intimidating, but stick with me. P is pressure. W is something called specific weight. Just think of it as density. V is velocity, how fast it's going. G is gravity. And Z is its height or elevation. What this tells us is incredible. For a perfect fluid, if you add up these 3 things at any point along its path, the total is always constant. It doesn't change. It's a perfect expression of energy being conserved.
So let's break down that first piece of the puzzle, the pressure head. Just think of this as the energy the fluid has just because it's being squeezed. It's that potential energy stored in its pressure, kind of like the tension inside a water balloon you're about to throw.
Next, we've got the velocity head. Now this one's pretty intuitive. It's the energy the fluid has simply because it's moving. The faster the fluid is flowing, the more kinetic energy it has. Simple as that.
And the last piece is the datum head, which is Z. This is all about the fluid's potential energy because of its height. I mean, water at the top of a waterfall has a lot more potential energy than the water at the bottom, right? So you see, Bernoulli's equation is this beautiful balancing act between pressure, velocity, and height. If one goes up, another has to come down to keep that total constant.
Okay, that's enough of the abstract stuff. Let's actually visualize this with the simple pipe, and I promise it'll all click into place.
Okay, picture this. We have a fluid, let's say water, flowing nice and smoothly through this pipe. As you can see, it's wide at the ends, but it gets narrow there in the middle, kind of like a throat. Let's see what happens to the energy as the water gets squeezed through that tight spot.
Well, think about it. If you have the same amount of water trying to get through a smaller opening in the same amount of time, what does it have to do? It has to speed up. It's just like putting your thumb over the end of a garden hose to make the water spray faster. So where the pipe is wide, the velocity is low, but in that narrow section, the velocity is high.
All right, now let's bring Bernoulli's equation back in. Since our pipe is just sitting there horizontally, the elevation or datum head isn't changing at all. But we just saw that in the narrow part, the velocity shoots way up, meaning the velocity head increases. So if the total energy has to stay constant, something else has to go down to balance it out. And that something is the pressure. This is the magic of Bernoulli's principle. Where velocity is high, pressure is low. That's the secret.
Now, this whole inverse relationship between pressure and speed, it's not just some neat party trick for physics class. It is incredibly useful, and engineers rely on it every single day. Let's check out how.
So Bernoulli's equation is the backbone for a ton of practical devices. We're going to zoom in on 2 of the most important ones used for measuring how fluids are flowing, the Venturimeter and the Pitot tube.
You know that pipe we were just looking at? Well, that's basically a Venturimeter. By carefully designing a pipe with that specific narrow throat, engineers create a pressure drop that they can predict. All they have to do is measure the pressure in the wide part and compare it to the pressure in the narrow part. That difference in pressure tells them exactly how fast the fluid is moving, which gives them the flow rate. It's a really clever and direct application of the principle.
And then there's the Pitot tube.
It's just a simple little L-shaped tube that you point directly into the flow. The genius of this thing is its simplicity. It literally brings the fluid to a dead stop right at its opening. In that moment, all of the fluid's kinetic energy, its velocity head, gets converted into pressure. So by measuring that spike in pressure, you can work backward to figure out the original velocity. And yeah, this is exactly how airplanes measure their airspeed.
All right, so we've covered the theory, and we've seen it in action out in the real world. Before we wrap this up, we need to talk about the fine print and do a quick recap of the most important points.
Now, it is super important to remember that this version of Bernoulli's equation has some rules. It's designed for a perfect or ideal fluid. That means we're assuming a few things: that there's no energy loss to friction, that the flow is perfectly smooth and steady, and that the fluid's density never changes. Of course, in the real world, these things do matter, but this ideal equation gives us a fantastic starting point for almost any analysis.
So let's boil it all down. What are the 3 things you absolutely need to remember? Number 1, Bernoulli's principle is just the law of conservation of energy, but for fluids. Number 2, the big relationship: as speed goes up, pressure goes down, and vice versa. And number 3, this isn't just theory. It's the fundamental idea behind real, essential engineering tools that we use every day.
And that brings me to one last thing to think about. We've been talking about an ideal fluid where no energy is lost. So what happens in the messy real world? How do we have to change Bernoulli's equation to account for all the energy that real pipes and real fluids lose to friction? Well, that's the next step on the journey to truly mastering fluid dynamics.